Welcome. In this recording I would like to illustrate the approximation of the individual risk model by the collective risk model. Consider the following situation. You have a portfolio of N life insurance policies. For each policy you have an individual I, and this individual has a probability Qi of dying and an insured amount Bi. The total claims in that situation are the sum for I from 1 to n of II Bi if II is 1 if the individual dies, so with probability Q1, and 0 otherwise. This is the individual risk model. If Qi was a constant, the same for all the individuals, and they had all the same insured amount, then S tilde would be binomial with parameters n and q once scaled by the insured amounts. But of course this does not happen in reality. So if this is not verified, otherwise you need to do the n convolutions. Even if the distribution of II Bi is relatively simple, you still have to do n convolutions, which is rather tedious. Of course, you could say, well, I'm considering only the individuals that have the same age and sex, and they have the same probability of death, and have chosen the same amount, same insured amounts. In that case, you could calculate that as a binomial random variable. But then how do you aggregate these smaller sub-portfolios into your big portfolio of life insurance policies? Then you still need to do a certain number of convolutions. So consider the following approximation. We approximate S tilde by a S, which would be a sum of n random variables yi, and these yi I defined as ni bi, with ni being a Poisson random variable with parameter lambda I. So ni has range 0, 1, 2, 3, and so on. But in this case, since lambda I is a probability, well, I mean, yeah, since lambda I is the average number of deaths for this individual per year, this will be very low, and most of the probabilities will be around 0 and 1. But you still have these possibilities that are not really possible in reality. So that's where the approximation lies. Here we replace IIBI by NIBI. II is either 0 or 1. Either you have survived or you have died. NI is Poisson, but you can survive, die twice, die 3 times, die 4 times, and so on, which is of course not possible. But this is negligible for a small lambda. So you have two possibilities for lambda I. The first one is that we want the expected value of Ni to be equal to the expected value of II. Okay, we have replaced, basically we have replaced II by Ni. So it seems natural to want these two, the expected value of these two random variables to be equal. This means that Qi will be equal to lambda I. Lambda I is the expected value of Ni, and Qi is the expected value of II. This leads to the canonical model, by the way. Another thing you might want is that you want the probability of survival to be equal in both cases. Here you have mainly two big probabilities at 0 and 1. So in this case here, you want the probability that of survival to be equal in both cases. So this leads to lambda I of minus the log of 1 minus Qi. But this is, you can verify that this is more than Qi. So the advantage of this is that you'll be on the safe side in a sense, because you are overestimating your number of losses for each year. The probability of survival will be exact, but the average number of deaths will be overestimated. Okay. So let's develop this approach. We have an S that was the sum for I from 1 to n of yi. And this is n1 b1 plus n2 b2 and so on until n bn. And this is a collective risk model, and you can see that S will be compound Poisson. Thanks to the theorem 12.4.1. The sum of compound Poisson is compound Poisson. So here, N1B1 is in a sense a compound Poisson random variable with an amount B1. It's a degenerate random variable with outcome B1 with probability 1. So the parameters of S, lambda, here, lambda here will be the sum of the lambda i's. Whatever the assumption you make about the lambda i's, of course. And your distribution of the losses for your compound Poisson S will be the probability that the first, when you have, given you have a claim, the probability of that claim, the distribution function of that claim, is the probability that the claim comes from the first individual times the CDF of that first individual, then the probability it comes from the second individual times the distribution function for that individual, and so on. So if we examine these CDFs, they are all similar, but with a different claim amount. This one here will be 0 if x if less than the insured amount for the first individual, and then it jumps at 1 at x is equal to b1. You can also express that as an indicator that will be 1 if x is between b1 and the infinity, which explains the formulas that are on the slides in the lecture notes. So the advantage of that approach is that you can now aggregate portfolios easily, because here you have your life insurance portfolio that you have approximated with this compound Poisson collective risk model, and maybe you have another portfolio of another type of risks, and you can aggregate these two portfolios thanks to the properties of the compound distributions. Also, I can calculate the distribution of S using Panger easily, rather than doing n convolutions. So that was an illustration to put the approximation of the individual risk model by the collective risk model in perspective.